Yesterday we talked about the derivatives of natural log of u. So that's logarithms. Today we're going to talk about the derivatives of e to the u. So e to the u is a specific type of exponential. Remember, exponentials are anything of the form a number raised to x. So it could be 2 to the x or 3 to the x, or as we're using, e to the x. Any of those are exponentials. So the exponent has a variable. Okay? So the rule for the derivatives of e to the u is very simple. It's itself times the derivative of the exponent. Itself times the derivative of the exponent. So let's do a few examples of this. Let's say we have f of x equals e to the 2x, and we want to find its derivative. Well, it's itself times the derivative of the exponent, and the derivative of 2x is 2. You're welcome to leave it like that. More normally, we'll actually put the 2 out front and write our answer like this. And that's all there is to it. It's itself times the derivative of the exponent. In fact, let me write that down. Itself times the derivative of the exponent. So it's e to the u du, in other words. E to the u du. Okay, let's look at some more examples. Let's do e raised to, our original function f of x is e to the x cubed minus 5x. So for our derivative, it's itself, so we just rewrite the exact same equation, times the derivative of the exponent. Well, the derivative of x cubed is 3x squared. The derivative of negative 5x is negative 5. And that's our answer. Alright, now I want to show you the coolest derivative ever, and that is e to the x. Some of you are already probably seeing where this is going. If we take the derivative, it's itself times the derivative of the exponent. Well, that's just 1. So e to the x is its own derivative. Alright, now I realize that may not sound really cool, but here's what that means. If you plug 1 into e to the x, it obviously tells you the y value. Like if I come back here, plug in 1, e to the 1, it's 2.71 something. Well, it turns out that not only is that the y value at 1, that's also the slope at 1. And thinking forward a little bit, if the derivative is itself, then so is the integral. So that also tells you the area under e to the x from 0 to 1. So e is a pretty amazing function because its y value not only tells you the slope at that point, but also the area from that point back to 0. Or really from 0 up to that point. So, cool function. Alright, now let's try x cubed times e to the 2x. So here we have to use the product rule because we have two different functions being multiplied by each other. So our f will be x cubed and our g will be e to the 2x. Obviously the derivative of x cubed is 3x squared. The derivative of e to the 2x is 2 e to the 2x, or let me write it the way we have been, itself times the derivative of the exponent. So really just 2 e to the 2x. F prime times g gives us 3x squared e to the 2x plus f times g prime. So x cubed times 2 e to the 2x. So we'll say that's 2x cubed e to the 2x. Just so you know, you could write it as x cubed times 2 e to the 2x. That's not wrong. You're multiplying, so it doesn't really matter what order you put things in. But just by convention, the 2 would come up front. Any coefficient just comes up front. And usually the e comes after the x, but that's less certain than the 2 being up front. Again, that's just kind of by convention what people normally do, not necessarily what's mathematically necessary. Alright, now we're going to do one more. And this one's a little more difficult. We're going to do f of x is equal to the natural log of 2e to the x over 1 minus e to the negative x. Alright, so really what's happening here is we're going to have to combine what we learned from yesterday with what we've learned today. So we're combining our log properties, our log derivatives, and our e derivatives. So first, I don't want to use the quotient rule if I can help it, so I'm going to split this up into 2 pieces. So notice, this is still the original function, and I get that. Now, when we take the natural log here, remember the derivative of a natural log is the derivative of the inside. Well, the derivative of 2e to the x would just be 2e to the x over the inside, which would be 2e to the x, minus, okay, we do the derivative of the inside. The derivative of 1 is 0. The derivative of negative e to the negative x would be positive e to the negative x. And that's because it's itself times the derivative of the exponent. The derivative of the exponent is just negative 1. So it would just change the sign back to positive in front of the e, divided by the original. Okay, and obviously there is one spot here we can simplify. 2e to the x over 2e to the x is just 1. So we get that. And just to stretch ourselves a little bit, why don't we find a common denominator here and combine? Because 1's pretty easy. 1 would just be 1 minus e to the negative x over 1 minus e to the negative x. Okay, so on top we have 1 minus e to the negative x minus e to the negative x, so it'll be 1 minus 2 e to the negative x over 1 minus e to the negative x. Alright, so here's the one form of the answer, and that's fine if you got that far, and here's another form of the answer. Like I said, they get a little tougher when they start combining the natural logs and the e's. You just have to make sure you keep your rules straight. Remember, natural log is du over u, derivative of the inside over the inside. E is itself times the derivative of the exponent, which is e to the u du. Okay, now that you've got these new rules, if you want to practice these some, I'd recommend looking at page 348 in your books, number 40 through 58 even. You can also try the odds if you want and check those in the back.